Imagine a breathtaking megastructure floating endlessly through the vast expanse of space, beckoning humans to explore and inhabit its vast corridors. What if we could one day establish an orbital settlement hundreds of kilometers from Earth, or create a colony closer to the Moon or in the asteroid belt beyond Mars? The possibilities are endless, and the excitement is palpable. But the journey to creating a space colony is a daunting one. In order to sustain human life in space, we must design habitats that can withstand the harsh and unforgiving conditions of the cosmos. These habitats must provide a safe and comfortable environment for generations of human settlers and have replenishable sources of food, water, and breathable air. They must also spin to produce artificial gravity and protect their inhabitants from the harmful effects of solar radiation. The sun releases a continuous stream of charged particles called solar wind, and in deadly bursts known as solar particle events. Meanwhile, cosmic rays and charged particles pose additional radiation risks. In the face of these dangers, we must develop innovative technologies and designs to create space colonies that can support human life and protect our explorers. Join us as we explore the cutting-edge science and engineering behind space colonization and imagine what the future may hold for humanity in the final frontier. Among the many challenges faced by space scientists, none has been more formidable than the creation of a fully functioning space station that can accommodate the needs of humans living and working in microgravity. In 1988, the first modular piece of the International Space Station, ISS, was launched into orbit, and over the next 13 years, a team of international astronauts and engineers worked tirelessly to piece together a groundbreaking microgravity research laboratory that floats roughly 400 kilometers above the Earth. The ISS orbits our planet every 90 minutes, reaching speeds of up to 28,000 kilometers per hour. For more than 2 decades, the ISS has remained a remarkable feat of engineering and exploration, safely accommodating teams of astronauts who have spent months and even years in space. However, the ISS is not a permanent or self-sustaining habitat, nor does it provide a comfortable environment for scalable colonization. Astronauts must subsist on vacuum-packed or freeze-dried meals, and the cramped living conditions and prolonged exposure to weightlessness can take a serious toll on their physical and mental health. Explore the potential of human colonization beyond our planet with insights from the International Space Station. Though not a permanent settlement, the ISS has contributed valuable knowledge to our understanding of life in space. To build a larger, self-sufficient space structure capable of supporting colonists, we must develop a closed-loop life support system that recycles water and generates oxygen. The ISS has tested a breakthrough environmental control and life support system, ECLSS, that maintains temperature and air quality in habitable cabins. 2 devices on board generate oxygen by electrolyzing water while simultaneously removing carbon dioxide and other volatile gases. Over the past few years, the European Space Agency has tested a unique life support system that processes 50% of CO2 on the ISS to generate oxygen. The photobioreactor, designed by German scientists, leverages photosynthetic algae that consume CO2 and release oxygen in the presence of light. It even produces biomass, a step towards creating replenishable food sources for astronauts. While this is a significant development, the ISS still needs to rely on oxygen tanks for emergency storage and use in spacesuits. The station is unable to pressurize generated oxygen to support astronauts on spacewalks and regularly requires shipments of nitrogen, the most abundant gas in the cabin air. As space exploration advances with missions like NASA Project Artemis, life support systems will continue to improve. Designing a closed-loop system for a space colony has been a challenge for over a century, but some of the most influential ideas came from the mid-1970s. Back then, physicist Gerard O'Neill proposed constructing massive orbital cities that could potentially house millions of people. His O'Neill cylinder design features 32 kilometers long and 6 kilometers in diameter cylinders that create artificial gravity by rotating on their axis. These cylinders could encase artificial terrain, yielding 1,300 square kilometers of living space, and even support thriving natural ecosystems. Another innovative megastructure, the Stanford Torus, is a donut-shaped habitat with a hollow residential tube where 10,000 colonists could live in a ring held in place by rotational gravity. The Bernal sphere, O'Neill's downsized version of the cylinder, is a globe less than 2 kilometers in diameter that rotates more quickly to produce Earth-normal gravity. These designs have inspired many more concepts in the 21st century, such as the Kalpana 1 orbital settlement proposed in 2006. Kalpana 1, similar to O'Neill's cylinder, employs rotating cylinders to simulate Earth-normal gravity. The structure features end caps that provide a continuous source of light and solar power, along with radiation shields that protect colonists. Unfortunately, constructing and transporting materials for a space colony is expensive, making it difficult for many organizations to undertake such projects. Scientists propose innovative solutions to reduce the cost of construction and transportation, such as using lunar regolith as building material for colonies near the moon and 3D printing technology for constructing colonies in the asteroid belt. Although it is unlikely that an affordable and replenishable habitat will be created in the coming century, new hyper-efficient designs may accelerate humanity's push towards space colonization. While our society is currently bound to Earth, our descendants may one day live amongst the stars.